Sorry about that. My computer ran out of batteries in the middle of the explanation. So let's go back a little bit. So what I was trying to explain now was the step here. I mean, when I said that this quantity here was smaller than 2 times the absolute value of c plus 1, provided if x minus c in absolute value was less than 1. And this followed because of from the triangle inequality, because x plus c is the same as x minus c plus c plus c. Right, so we use the triangle inequality here, and this is less than or equal to x minus c plus 2 times the absolute value of c. This is less than 1. This whole thing is less than 2 times, strictly smaller than 2 times the absolute value of c plus 1. So this concludes the proof of the proof that the limit of f of x as x approaches c is c squared for f of x equals x squared, the function x squared. This is basically how we proceed. So as I mentioned before, these steps here that allows us to bound things from above are things you need to collect at the end, so as to make sure that all the conditions are satisfied. So here you need to find an epsilon, a delta that works for that epsilon. So here you've made two assumptions, right? You've made the assumption that x minus c is smaller than 1, and also smaller than epsilon over 2 times the absolute value of c plus 1. So to conclude, we just mentioned, so we see that delta, and of course if you're assuming that x minus c is smaller than two things, in order to ensure that both things are satisfied at the same time, then you just pick the smallest one of the two conditions, and that will, of course, as long as x minus c is smaller than 1, this first inequality here holds, and as long as x minus c in absolute value is smaller than epsilon over 2 times the absolute value of c plus 1, then the last inequality will hold. So you need to choose delta smaller than these two things. So this is going to be the min between 1 and epsilon over 2 times the absolute value of c plus 1. Okay. So this is how you proceed. So usually when you in the linear case, we only had one condition. Whenever you were dealing with nonlinear functions, it is often the case that you'll need to make, in order to bound things, you will need to make different assumptions on the smallness of the distance between x and the point c. And so you need to put all of them together. So what happens in all of the examples, all the relevant examples for you, is that you only have to make finitely many choices. Finitely many constraints. So you have to make them, say 2. Typically there are no more than 2, but the 2, 3, maybe. And then at the end you need to choose them. So that tells you how small delta has to be. Delta has to be smaller than 1, and also delta has to be smaller than this other quantity here, than this quantity here. And so in order to make sure that that everything here is valid, so all the steps here are valid, you need to pick the smallest of all between all these quantities. which since there are finitely many, they still give you a positive number. And well, it usually ends up being the case that the last condition is the one that's really active, in the sense that if epsilon is really small, then of course the minimum, I mean for epsilon really small, the second quantity here is going to be smaller than 1, so this delta is really just this quantity here. But for the sake of being rigorous, yeah, if the given epsilon was very large, then 1 would be smaller than epsilon. Then epsilon over 2 times the absolute value c plus 1. But usually it's another case. I mean, the continuity, convergence, and all these things depend on. I mean that you see you test things really when epsilon is small, not when epsilon is big. Okay, so that's what had to do with I mean these examples about showing the limit of f of x is some quantity as x approached some value c. Then the next thing we need to do is cover the sequential criterion for functional limits. This is what I said before. That is, I mean, usually the definition of continuity, depending on the textbook, is one of the two statements. The one we've given here, we're using epsilon deltas, and the other one involving all sequences that converge to a point, and the limit of the sequence f of x n. I mean, where xn is the sequence, it's a given sequence converting to the point c. And this is what we're going to do next.